Hello, everybody. I discovered after class that my videos from yesterday were lost because YouTube changed how they do their streaming and I did not have the right configuration set up after the change. So I am re-recording what was covered yesterday in terms of new content. That way everybody can catch up who wasn't able to attend the class. I am right now making sure that my stream is actually going because this is the second time this morning that I have tried to do this. So it says it's going. I hope to be able to actually finish this lecture. So thank you for joining me. I'm going to be picking up on slide 38 of lecture 2, which is where we started yesterday. The earlier part of the class, we were talking about homework 2 questions, as well as the spreadsheet that I had posted about bivariate association, and so this slide actually covers the same information as the spreadsheet. If you have homework questions, please make sure to email me and I can help you. So, making sure that this is still working. Okay, it's showing me live. Let's do this. So slide 38. So concluding the unit that we've been focusing on with respect to bivariate association, the kinds of procedures that you would use to assess relationships between two variables depend on what kind of variables they are. So if you have quantitative variables, you can look at a linear association between the two of them using a Pearson correlation. And I note that there are special names for Pearson correlation here if you have a mix of binary variables. So two binary variables is called a phi correlation, and a binary with a quantitative is called a point biserial, but they are mathematically equivalent to Pearson. They just have formulaic shortcuts that are available when you have one of the variables as binary. So if you have two quantitative variables, Pearson's R directly is the effect size for the association, where 0 means there's no relationship and 1 is the strongest the relationship can be. If it's a positive one, that means as x goes up, y goes up. If it's a negative one, as x goes up, y goes down. If you are concerned about extreme values on your quantitative variables, or you have ordinal variables in which you can only talk about rank ordering, that is what Spearman's correlation is for. It is exactly the same as Pearson's correlation, except that the input data is different. What happens in Spearman's R is that the original variables are first converted into their rank order forms. So on a quantitative variable, the lowest score would be a 1, the next lowest score would be a 2, and so on. Ordinal variables, if they aren't already in that type of ordering system, would be converted as well. And then from there, a Pearson's correlation is estimated on the rank order versions. In either case, the accompanying significance test uses a t-distribution. So we're measuring the one association, that's numerator degrees of freedom 1, with denominator degrees of freedom that reflect our sample size. So t is going to be flatter with more area in the tail and smaller samples. And we get then a p-value that tells us what the probability is of observing an R that we did from our sample as extreme if the null hypothesis were true. And most of the time, a null hypothesis is zero correlation, but it doesn't have to be. For variables that are categorical, measures of association tend to be formed from contingency table analysis and result in Pearson's chi-square. So this one is different in that the direct result of the analysis is the test statistic, and you have to work backwards to be able to get an effect size. Pearson's chi-square needs numerator degrees of freedom for the number of cells in the contingency table that you need to know before you can figure out what all of the other cells must be given the marginal row and column totals. It does not use denominator degrees of freedom with respect to sample size, and so there are various alternatives to Pearson's chi-square, such as exact tests that pay attention to small samples. And I note at the bottom here that I skipped the combination of quantitative and nominal because those types of bivariate association are better handled in models because we have more than one possible association with each of the distinct categories of the nominal variable with the quantitative variable. So when we're conducting tests as to whether or not we have a significant association between two variables, we can screw up this process and make an incorrect decision in two distinct ways. So this is where we're picking up here. So just to recall the process of making that decision in the first place, we have some sort of reference distribution that goes with our test statistic. So if we're testing one thing at a time, that's what T and Z are for. Z does not use sample size, whereas T does. And if we're testing more than one thing, that's what F and chi-square are for. Chi-square does not use sample size, but F does. And we haven't met F yet, but he's coming. We have to decide where the line in the sand is for what is declared to be unexpected or significant. That is our alpha level. And the traditional alpha level we use in the social sciences is 0.05. I'm making sure that this video is still going. Bear with me. Okay, it looks like it's still okay. This is good news. Checking my stream, looks like it's still okay. All right. So if we say that we have alpha of 5%, what that means is that we are declaring 5% to be where unexpected starts. And in most cases, we want to have a two-tailed alpha. That implies that our result could be higher than expected or lower than expected. And so that's depicted in this picture here, which could be a T or a Z, a distribution that has both a positive and a negative side to it. If the result is more positive than expected, that can happen 2.5% of the time is the red area. If the result is more negative than expected, it can happen in the other 2.5%. And the middle part is where expected lies. So this would be a way to describe expected distribution uncertainty, expected sampling uncertainty. That's the word I want. Where you would get a result due to normal fluctuation across samples. This is where we would say that the result is not different than 0. The cut points tend to be around 2 on a distribution of T or Z. More specifically, if you have infinite sample size, the Z value of 1.96 would be the same thing as a T. In smaller samples, this value of 1.96 will be a little bit higher to reflect the fact that in smaller samples there's more area out here, so you have to get further out before you hit the magical 5% region. So if we find a result that is in these red areas that corresponds to a probability less than the alpha level, we reject the null hypothesis. We say it is unlikely that our result would have been found if the null is true. So given that setup, if the null hypothesis is our baseline, typically speaking, it's a null hypothesis of 0 association, but it doesn't have to be. The alternative then that's set up by the two-tailed test is that there is some association. And note how dreadfully unspecific that is. Just not 0. It could be anything, but it's not 0. So based on what we decide about the null, we have two different kinds of errors that we could make, and they correspond in general to false positives and false negatives. So if we reject the null, if we say that there is an effect, then we have to be worried potentially about making a false positive, a false alarm. So if the null is actually true and we reject it, that could be a wrong decision, and that's what's known as a type 1 error. So when in reality there is no association, but we say there is one, we say that the association is significantly different than 0, that could be a false alarm. And the proportion of times that that may happen is set as our alpha level. So when we choose an alpha of 0.05, what we're saying is that, yeah, 5% of the time we may declare something to be significant when actually it's part of the distribution for the null hypothesis, because even though it's unlikely, it still could happen. So if you want to be more conservative, you would lower your alpha level so that false alarms would be less likely to happen, maybe 1 out of 100 instead of 5 out of 100. If you want to be less conservative, you would raise your alpha level, making it easier to declare something significant, have a higher area in which you would declare something to be unexpected. If you are on the other side here, so if the alternative hypothesis is actually true, if there is an effect to be found, then you could miss it. That's how you could get it wrong. So A miss is what's known as a type 2 error. In stats textbooks, it's noted as beta, although in practice, no one talks about it that way. They either say type 2 error or they say its opposite, which is power. So given that there is an effect to be found, power is the probability that you find it. A type 2 error is the probability that you miss it. So these things are inversely related. Power and type 2 error are often described with these sorts of overlapping distribution pictures, such as the one that I borrowed from the internet here. And this is trying to make the point that one of the ways that you can improve your power, that you can make it more likely to detect an effect that is actually there, is to increase your alpha level. So if you make it easier to find something to be significant, if you increase the area that you're willing to say unexpected lies in, then that has the result of increasing your power. But power really has to do with the alternative distribution, not the null. So I think it would be easier to understand with a different perspective. So I did another simulation to try and demonstrate this a little easier, more easily. So I'm going to play God. I'm going to generate another 100,000 fake people where I know what the right answer is. More specifically, I'm going to generate two variables that each have a normal distribution, so what's known as bivariate normal, in which the true relationship between these two variables, the population correlation rho here, is 0.3. So that is truth. I've got a population where I know what the right answer is. The correlation is 0.3. And I'm going to draw repeated samples of a finite size from this population distribution, and I picked sizes 42, 63, and 85. Now those seem to be arbitrary numbers, but there is a reason, so stay tuned as to why I picked those in particular. So these pictures on the left here, these histograms, show the distribution of what the sample correlation ended up being in each of these 1,000 replications. So I grab a sample of 42 people, I compute the correlation. Grab another sample, get the correlation. So these pictures show the variability in what those correlations ended up being. And I've highlighted the right answer as the middle here. The blue lines are over the 0.3 population value. And you can see that on average, we get the answer right. But the devil lies in the details. On average doesn't guarantee what's going to happen in any one sample. And the fewer people that you have, so in a sample size of 42 relative to the others, the more variability there is in what the correlation could be in any one sample. So for 42 people, my sample correlation was anywhere from about 0.7, which is way too high relative to the 0.3 it's supposed to be, all the way down to potentially a negative 0.3. So a lot of variability here in what you would actually get. That variability decreases. The distribution gets more compacted as you increase your sample size. So in larger samples, there's less wiggle, there's less inconsistency, there's less variability in what the correlation would be in any one sample. And so then, given these results, we can talk about power as the probability of rejecting the null hypothesis, given that there is an effect to be found, which is what we know is true because I made the data. So for each of these correlation estimates for each of the samples, I then computed the corresponding t-test statistic, and those t-test statistics are what's shown on the x-axis down here. So recall that in getting a t-test statistic for a correlation value, the only other thing you need to know is n. So given correlations of the same value, of the same effect size, smaller samples are going to lead to lower t-values, whereas larger samples will lead to higher t-values. So I have broken up this distribution into chunks here based on whether or not for any one replication you would decide to reject the null hypothesis. So a t of just over 2 in the case of 42 people, t closer to 2 in the case of 85 here as our boundaries. So any t-test statistic that would be smaller than -2 would be declared significant, a significant negative correlation in any one sample. That didn't happen. In the middle of these red boundaries is lies the replications in which t was within the area that's expected, so not different enough from the null hypothesis of 0 to be declared unexpected or significant. And so these are type 2 errors. So they are situations in which we know the sample came from a population with a true effect of 0.3, but we don't have a strong enough estimate in the sample to say that that correlation is different than 0. So this is our type 2 error range. The samples that did cross the dividing line, where a t-test statistic would be positive, so a t greater than 2, the proportion of replications where we would reject the null hypothesis, we would say the correlation is different than 0, this is our statistical power. And what you can see as we move across these sample sizes is that more and more of the distribution is on the power side and less of it is on the type 2 error side. More specifically, statistical power is 50% if I have 42 people given a correlation of 3. So half the time in any one sample, I would reject the null hypothesis or I would not reject. It's 50-50. The percentages of power increase as sample increases, and the opposite of power, type 2 error, decrease. So for 85 people, the last picture here, about 79% of the replications had a strong enough signal to reject the null hypothesis to say the correlation is not 0, and 21% of the replications didn't. So this is known as statistical power. What is the proportion of times where you would expect to reject the null hypothesis given the population effect size and given the sample size? And in the social sciences, we try to shoot for power rates of 80%, which correspond to miss rates, false negative rates, type 2 error rates of 20%. So this is interesting given that type 1 error, alpha, is usually set to 0.05, type 2 error is set to 0.2. So we are more willing to make a false negative 20% of the time than we tend to be willing to make a false positive type 1 error 5% of the time. So why did I pick these particular sample sizes is because I was trying to demonstrate one of the results that's found in this table. So what this table is a description of the sample sizes needed to achieve certain levels of power at a given level of effect size. So I've given you a handout in PDF format that has 4 of these tables. So there are tables for R effect sizes, which is a correlation metric ranging from -1 to 1, and D effect sizes, which is a standardized mean difference metric where 0 again corresponds to no association, but there is no upper boundary. And I have tables for alpha of 0.05 or 0.01, so this is the table that corresponds to an R effect size at an alpha of 0.05. If you go across the columns, these are the values of the R effect size. So note that they range from a low of 0.1 up to a high of 0.9. We don't need negative values because negative just means that the pattern is opposite, but it's still the same strength of a correlation. So a correlation of negative 0.8 is the same strength as a correlation of positive 0.8. It's just a difference in the pattern. Down the rows is the rate of statistical power. So the proportion of replications at that sample size in which the null hypothesis of no association would be rejected. And I've highlighted the magical 80% row right here. So the values in the table then give you the sample size that corresponds to that rate of power for each effect size. And so I've also highlighted in the red here the sample sizes that I chose in the previous simulation. And damn if the results are not spot on. People who did the math for me, thank you for getting this right so that I didn't have to do this all via simulation. So for instance, given my population correlation of 0.3, if I have 42 people, half of the time in any one sample, I would reject the null hypothesis. If I have 63 people, 2/3 of the time, I would reject the null hypothesis of no correlation if the true correlation were 0.3, and get to a magical level of power of 80%, it takes 85 people. And that is almost exactly what I found in my simulation. So power analysis is generally described in textbooks as the process of starting with an effect size and then using that effect size to figure out what sample size you need to achieve adequate power. I am checking my video again just to make sure it's going to work. Okay, seems to be functional. So for instance, let's say that in previous research, I have come across articles in which two variables that I'm interested in are correlated about zero point 0.3. So I want to do a study to look at the same type of association. Maybe it's in a slightly different type of sample, or it's going to have other variables that haven't been measured. There's something that makes it new, but I've got something to start with respect to at least one of the associations, and I'm expecting an association of R of zero point 0.3. Well, then I go down the row here and I say, what is the N needed to get me to the 80% power mark? It looks like I need 85 people. If I want a smaller effect size as my target, so an R of zero point 0.2, if I go down that column, get to the row where the 80% line is, now I need 194 people. So even though it's just a small difference in correlation going from zero point 0.3 to zero point 0.2, it's a very large difference in the sample size needed to achieve the same rate of power, the same probability of rejecting the null hypothesis in any one sample from these populations. So if you look at the numbers in this table, you'll see that the sample size increases exponentially as you move to the bottom left here for smaller sample sizes at higher levels of power. So this is all well and good, but this is not typically how it happens in the real world. What typically happens is that someone comes to you for help with power and they say, I've got a sample of this. I've got a sample, say, of 30 people, and it's 30 people because that's all that I can afford to pay. That's all the time that I have to measure them. That's all the people that I have access to. For instance, 30 children in a classroom or 30 teachers in a participating school. So there's almost always some sort of logistical constraint that makes it so your sample size is the thing that is already determined. So then we can work backwards and do what is called a sensitivity analysis. So given my sample size, what is the minimum detectable effect size that I can get at an appropriate level of power? So for instance, if I said I can do 30, that's how many people I can do, what will that buy me? All right, let me go to my 80% power line, 28, okay, close enough. Then I would say that for 30 people, you can detect an R that is greater than or equal to zero point 0.5. That's what you can get. If you can somehow find a way to get, say, 50 people instead, that's going to bump you down to a minimum detectable effect size of zero point 0.4 instead. So you have better ability to find a smaller effect in a slightly larger sample. And so you can start with the numbers inside the table and then figure out what the minimum detectable effect size is. In practice, tables like these are appropriate only in a very limited set of circumstances for very simplistic analyses where you're only looking at, two variables at a time in an independent sample and that kind of thing. There are software programs that are designed to conduct power analyses for you, so you can give a more complex set of inputs. For instance, in a regression model, you can look at the power of the overall model as well as the power for any unique predictors, and you can run a program like gpower to give you power estimates. There's power packages within R, there's packages within SAS, there's all kinds of packages that have been developed to do power analyses for you. However, the types of situations in which those are useful are also relatively straightforward designs. In the work that I do, it is almost always the case that I'm going to have to do simulation to figure out what my empirical power rate is. That is to engage in this kind of process that I described here, where I make up data that is consistent with a given effect size, and I create fake people and fake samples to see how frequently I would declare a given effect of interest to be significant. So I may start with a fixed sample size and change the data until I hit 80% power and figure out whatever the magical minimum detectable effect size is. Or if it is a case where I have an effect going in, then I may manipulate the sample size until I hit the 80% mark. But it does require actual generating data with which to do this empirically rather than looking at ready-made tables. So that just wanted to show you sort of get a flavor of what power means, the idea that it's the probability that you'll find something that's actually there, setting the stage for type 2 errors, which is the opposite of power. So if I have this 80% power line, what I'm saying is that I'm willing to accept a 20% type 2 error rate. I'm willing to have a false negative where I say I don't have something, but I actually do have it for real. So there we go. So wrapping things up in terms of the information that you would want to give your readers about bivariate analyses. So if you're conducting bivariate analysis in the context of a model, you would have a parameter estimate. We don't have those yet, but we will soon. You will have the value of the test statistic to report, so our friends T, Z, F, or chi-square, and those may or may not have degrees of freedom that go with them. So for instance, T doesn't have either, or excuse me, Z does not have either. T has denominator degrees of freedom. F only has numerator degrees of freedom, or chi-square, excuse me, only has numerator degrees of freedom, and F has both. So the test statistic that you use will dictate what degrees of freedom are relevant to report for it. Your test statistic is going to give you a p-value that should also be reported, the probability of observing a result as extreme as what you did if the null hypothesis were true. And finally, an effect size. So if you're doing a correlation analysis, the R correlation is the effect size. If you're doing something like a Pearson chi-square for contingency tables of categorical variables, you have to back translate that test statistic into an effect size of some kind, such as an R, a risk ratio, or an odds ratio. And it's nice to include confidence intervals around those effect sizes if you're able to do so, such as we did in Proc Core, or there's a Stata package that does that, the Fisher R to Z transformation to get the confidence intervals around the effect sizes for those. So given your decision about significance, just to review the two kinds of errors that we can make. If you reject the null hypothesis, so if the null, for instance, is that there is no association, and you find an association that would be declared unexpected if the null were true, we say that the result is significant, that it looks like the relationship is not zero. In making that claim, we do have to worry about the fact that it could be a false positive. And the rate of false positive, your type 1 error rate, is your alpha level. You set that ahead of time. If you choose an alpha of 0.05, you are saying, I accept the fact that 5 times out of 100, I'm going to declare something to be not zero that is actually part of that zero null hypothesis distribution. Just because it's unexpected doesn't mean it's not possible. But you don't have to worry about a type 2 error or a miss. If you retain HO, so if you're in the do not reject, you say that the relationship is not different than zero, that it is well within expected sampling fluctuation if zero were true. If your p-value is greater than your alpha level, greater than or equal to, then you do have to worry about having made a type 2 error. You could have missed an effect that was truly there. So then questions of power are relevant. If you declare an effect to be non-significant, if you say that your correlation, for instance, is not different than zero, that could happen because there is no correlation. So the correlation effect size is very small, or it could happen because you don't have enough power to find it. You don't have a large enough sample. And so making sure to report your sample size and your effect size will help inform your readers as to which case is more likely at play in retaining the null hypothesis. Is it a power situation where there is something that's worth talking about, but you didn't have a good enough chance to find it because of a small sample? Or is it because there's no effect that is actually sizable enough to go find? So whenever you retain the null hypothesis, you declare something non-significant, you need to worry about power. You need to worry about type 2 errors or misses. Whenever you declare something to be significant, you do not need to worry about power, but you do need to worry about type 1 error. And that's my story. Next week, I will go over the article that I gave you as an example that illustrates these issues that I forgot to go over last time. So I hope to see you then. Until then, stay safe, stay sane, and have a great weekend.